Hello viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're gonna talk about wafer-scale CPU, meaning big ass CPU. So let's dive right into it. Now, what is the problem with our current mode of operation? Basically, we are reaching max miniaturization, meaning we have reached a point where we can make processor very small. We have reached a point where we can make transistor ludicrously small, as in like 7 nanometer, 5 nanometer. Some designs are in lab that can even reach 2 or even 1 nanometer. But reality is that the moment you start to go below this sort of threshold, the error rates due to physics starts to go up, meaning no matter what you do, you cannot change those things. You can work around them. You can have this or that or this hoo-ha or this GG, but reality is it's like we are reaching a point where it's no longer more feasible to try to make it even smaller, because like jump we went from 500 nanometer to 50 nanometer to 20 nanometer to 5 nanometer. Those are awesome, but 5 to anything below is not as amazing as people are that. And you can see that like Intel had such a huge issue, given the fact that it's one of the leading in semiconductor industry. They had such a huge issue with basically trying to shrink it any smaller. Same happened with Samsung, same happened with TMC. Every company is struggling, and these are physics-based system, meaning you cannot bypass it. It's not the poor engineering. No, there's a physics-based issue. So we are reaching max miniaturization. Can we miniaturize it more? Yes, but not to a very large extent. Basically, do not expect to like the same jump we had from 500 nanometer to 50 nanometer. That's not gonna happen anymore. So at the core of it, you may be like, what are other issues that we are dealing with? We are dealing with electron speed, meaning when you connect one system to another system, you are dealing with a system where it has to convert everything to electron. Basically, competition is happening to electron, and it has to transmit that data from, let's say, one node to another node to another rack. All these hops is limited by physics. These things are limited by electron speed. Electron does not travel at light speed, so it does have latency. And you can literally have a scenario basically where you have a giant server farm. One node talking to another node could literally take milliseconds, and that's a very serious issue. So connecting many units, you may be like, okay, you want a higher grade supercomputer, just add more cores to it by adding more nodes to it. That's how we are doing it. But it's not as easy as you would think. There is an inherent limitation from every step of the chain, where it's like, how big can you make it? It's like, it's one thing to talk about like, hey, I'm gonna have, let's say, 100,000 cores. One thing to talk about. The moment you start to say a million cores, people like, it might not work as you think. And bandwidth, latency, these things starts to become bigger and bigger issue the more bigger you start to make your farm, so to say. So, and these things are physics based. You cannot bypass this. You may be like, I'm going to use optical fiber links between these two things, but here's the deal: optical does not work on magic. It still has to take electrons, convert into photons, then do the same thing again. So inherently you will be limited. So that's things become such a big issue that computer will literally go idling, meaning the clock cycle will be just like, I have sent a request for data, I'm waiting for it to come. So that simply creates a big overhead, and that overhead will literally eat away your electricity for no reason. It's just like, yeah, your CPU is like idling for lols. So that's a very serious issue. Now you may be like, we have been running this sort of architecture. Every supercomputer made are for this, and they are capable enough. They are predicting weather with surprisingly good accuracy. So what's the problem? It's like, if this works, it's a known system, everybody knows how it works, we have ecosystem, infrastructure, everything sorted for it. What's the issue? Well, issue is that we have a new challenger at this point in time, meaning training for computational AI. Meaning AI generally have two segments to it. A, you train the AI. B, AI implements something, or what we call inference. Now inferencing AI can be done on very low grade equipment, meaning your smartphone. It can do that. It can, like, it has the data, neural network data, and it can feed the camera data to the neural network. Neural network will spit out the data. It's like, hey, I think it's a dog, and your camera will be like, okay, you are taking a picture of dog, let me apply sharpen filter, whatever have you. That's one thing. We are utilizing that. That same thing happens on your self-driving car. It's like, it looks at it, it sends that, camera looks at the data is sent to the neural network feeds out the data. It's like, I think this is a car, I think this is a truck, and I think you should avoid this. Awesome. But what goes behind training those neural network? Supercomputers. And that's the issue. The demand of artificial intelligence is going ludicrously high. So the amount of training we have to do to these things is also idiotically high, meaning you are talking like billions of dollars spent just to train an AI. And not to mention, our computers are literally showing its age. It's like, I cannot compute this. Like, that's a serious limitation. So what's the solution? Well, solution is basically go big ass, large CPU basically, and you can have as many cores as you can get. And be mindful, when I'm talking about large CPU, I mean large CPU. Now you may be like, okay, why we are limited to this? Why can't we go as big as solar panel? Well, silicon that is needed for this sort of basically chip manufacturing is absolute purity, meaning ludicrously pure. So we grow them into what we call crystal ingots. Basically, you send that, you start to see it starts to grow. Now that grow, we try to make it as large diameter as possible, but there is a limit, because if you start to make them very large, they will still be good, but problem is they will have way too more like ludicrously high defects. So there is a optimum balance. It's like if you make the crystal this large in cylindrical system, everything was nice. Now this cylinder will be sliced up into wafers. That wafer will go into a lithography machine where it's gonna like do all the magic sauce to it. So this system is basically one wafer itself. Now this puppy is gen 2 of that. This is around 2.6 trillion transistor. I don't even want to count how many zeros that has. And it has, it's like the core count is so ludicrous that they are like, yeah, up to 1 million core. Up to 1 million core. Like, to give you a context, most people are familiar with like dual core, quad core, octa core, 12 core, or 100 cores, like if you're dealing with server, 200 cores if you're dealing with bit of a future equipment. The moment it starts to go 1000 or 2000 cores, that's something that the GPU has. Like high-end GPUs, enterprise grade GPU can easily go to 8000 or 10,000 million core. Take it and go. Like, that's a whole different level. Now be mindful, no amount of engineering, no amount of technology can give you absolute certainty. So these things will still have faults and defects, but the software is designed in such a way that unless the defect is too huge, it can route around it. So that's why like the million cores, it's not an absolute number. Like, they can have a chip that is like, they will rate the performance to like 90% of it, and they'll make sure that all the errors are within that 90% margin. So not all the cores will be working at absolute perfect, but like for all testing, all utilization, it will be the rated speed. So it's like, don't worry about it. It's like how Tesla gives you like every electric vehicle has a bit of buffer built into it. Same is here also. It's like there is a bit of buffer built into it, because you cannot grow a silicon crystal that is absolutely pro. You cannot build a machine that will never make a mistake. You cannot do those things. So fundamentally there are some limitations to this, and the biggest benefit of this puppy is basically it reduces travel outside the node, meaning data is coming in. Okay, everything is awesome, but data is coming through basically low bandwidth, high latency link. It's coming in. Okay, slowly, no problem. The moment data goes inside this, it does not have to comp out, because inherently it has around million cores. So it will do the complete data crunching on itself. It does not need to send the data to another system. It does not need to send data anywhere else. That's the core aspect. Data comes in, processed data goes out, and that is the biggest leapfrog technology in this puppy. Basically, you will go from I send the data, it's processing one part of it, that another part is processed in somewhere else, another part is processed somewhere else, and then all that is compiled in another server rack, and then it's processed into final compiled data. This is like, I got this. You feed the data, it's like, I got this. And that's a very big deal. And even if you have a requirement where you need multiple of this, let's say 10 of this or 20 of this, it's still a much data would be processed to much large extent. So parallelization would be much more simpler, because it's far easier to parallelize something that is going to, let's say, 10 system rather than 10,000 system inherently. So that's why this is an amazing breakthrough. And it also reduces the components, what we call auxiliary components. For example, motherboard. Whenever you talk about server racks, what do they have? They have processor. You count processor, it's like, oh, it has 10,000 processor, 20,000, but it's not like processor is just dangling there. You have processor, you have motherboard, you have RAM sticks, you have basic onboard flash memory or something. You have to have that. You have networking chip. All that overhead on just to access that processor, all that garbage that you have to have, that inherently increases your cost, your power consumption. All those things are really not good. Now this puppy has lower power consumption. Now this puppy can go up to 20 kilowatt. What Tesla is talking about is around 15 kilowatt. Now I'm like, wait a minute, I'm talking about processor, and I'm talking in kilowatt, and somehow I'm saying these things are efficient. How? Well, think of it this way. If I say 1 liter per kilometer for your car, it's very bad. But the moment I say 1 liter per kilometer for your train, it's like, dude, shut up and take my money. That's free. So that's the reality of it. The amount of computation these puppies can do, because it does not have like, let's say, even direct comparison, they are like at least 100 times smaller. So you do not have 99 motherboard, you do not have 99 RAM sticks, bare minimum. You do not have 99 this or that on network infrastructure and all that. Just remove all that. Not only you are making it smaller, you are also making it power efficient. And because the heat is concentrated in such a small area, it's ironically easier to take that heat away. It's like distributing, like if you have a lot of small things that are heating up at high temperature, it's very difficult to cool. But you have like one hot element, just have a, like how Tesla is doing, giant copper plate is like done. So that's the whole point, lower power consumption. So like a D1 chip has like power consumption of 400 watts, like 1 unit of Tesla's equivalent. This has a much higher component. This has like 1 unit. That 1 unit is 400 watt. To give you a context, even server processors are like around 200 or 300. This puppy is like really hot. But the amount of computation it can do, like for example, 362 teraflops, that's bonkersly high. Bonkersly high. So that's the solution that we are approaching at this point in time. Now, are there any risks in this sort of approach? Well, absolutely. Minor defect can ruin the whole wafer. Now, these wafers are multi-million dollar equipment. These are not something that most common mortal can even see. They are expensive, and you can have faults. I specified machines can have faults, but how big of a fault would be? Like you can design a software. It's like, okay, I can sacrifice let's say 10% of the cost. But what if the wafer got cracked, or when you are trying to cut it temporary? Things happen. This is a real thing. It will happen. It does happen. So you have to throw the whole disk away. And if you are ever familiar with like why the heck camera industry has APS-C sensor, it's like it's supposed to be full frame. That's what we went from, like full frame, basically film camera, to full frame digital camera. Why the heck we did not went to there and we went to APS-C? Because this technology was so expensive that back in the day when we were making sensors, they knew for a fact they can try to make full frame sensor, but because the waste issue was like basically you had a minor defect, you had to throw that whole thing away. That was so high that it was just not economical. Now if you start to make smaller units, the likelihood you still have to throw away would be very high, but you will get far higher working options out of it. So that's why people like small sensors. So going whole wafer, like it's not even like you have 3 sensors or 4 sensors or 4 or 5 processor unit, like whole wafer or nothing. It's all and in nothing. It's very risky inherently, like that's physics based risky, and it's not suited for everything. Many times people will say like this is the next big thing. Yes, it is the next thing, but not for you or me. It's not something that you're gonna see like in the future somebody's gonna open the modern smartphone and like giant multi-inch sensor processor. That's not happening. It's not suited for that. And it does require everything to be custom. That's a very big issue. That's why people abandoned custom build hardware for supercomputers long ago. That was the main issue. It's like you can just go to any manufacturer and be like, hey, can you give me 10,000 ROM processor? They're like, okay, I got you, fam. But you cannot do that with this sort of equipment. It's like, yeah, you have to build everything from scratch by yourself, meaning literally Cerberus is the only company that can do this. And they may be in a scenario they'll go to TMC or to Samsung. Hey, can you mass produce this? Yes, they can do that, but can Samsung build it themselves? No, because they have to build the operating system, the kernel, the whole platform cooling, meaning this puppy is such a high level cooling that it can cool down a good car engine basically. That's how good of a cooling this system is. So all these things, like this has the cooling unit in behind, and the power delivery system is bonkers. It's like it has 12 power system modules. It's like even 1 or 2 of them can fail and it will still keep working. So reality is everything has to be built from scratch. Everything. The only thing that is standard in this is the networking option. Other than that, everything is custom built. So that is a serious risk. You can build it, you can even have it, but people may not want to invest in it simply because, hey, it's too risky. I do not know, my technician do not know how to look at it, how to operate it, fix that. So that's a serious issue. It's not just like it's suited for everything. No, if you need this, then this is awesome. If you do not need this is not something like the next big thing for most people. For AI training, GG. For everything else, you can use it, but unwise. So what about deployment? Like that's the idea. Has it been actually deployed? Well, yes, this is the first generation of Cerberus wafer. Now it was awesome. It worked. To give you a context of that, it was when it was built the biggest single CPU, and the second generation is bigger than this. That's why it's right now not the biggest. Second generation is bigger than this, and this puppy was sent to National Energy Laboratory, if I'm not mistaken, and they run simulations on combustion system and all that. It was running combustion simulation on a power plant on real time. Let that sink in. A physics-based simulation running real time. How the heck that was possible? Because it had million cores. That's the reality of it. It's just like it has so much, and it does not have to wait. Like one core is not. Can you send the data there? It's like, hey, oh, okay, that data packet came here. Okay, so process. It's not doing that. It's doing everything inside that. So latency goes from like let's say 1 nanosecond to 1/4 of a nanosecond, or even actually 1/100th of that. So the nanosecond is the wrong unit for that, but you get that millisecond to nanosecond. That's how much time you are saving each data packet, because the data packet never has to leave this puppy. So data comes in through low bandwidth, it gets processed and spit out the final detail. So it was very powerful, and they created a comparison. It's like how big of a supercomputer you need to beat this. Well, reality was like ludicrously high. Like you could barely reach that, and because of the latency limitation, you technically can't do that. Like you can run a much higher detailed simulation than this puppy on other supercomputers, but they will never run real time simply because of that latency issue, and that's physics based. You cannot bypass that. So that's why like people are serious about this puppy. And Cerebras have already made the Gen 2, the image that I've showed before, and Tesla is also doing something similar. Now their approach is a bit different. Their approach is like, let's make a CPU dedicated for ourselves. Okay, awesome. That is the D1 unit. That's what you're saying. Now what you're saying, you may think this is a wafer scale computer. It's not. It's basically somebody came up with the idea. It's like when you look at a supercomputer, all you're counting is like graphics card, processor. Let's just focus on the processor. It's like, okay, this has this processor, but you never see that. Like you will count that rack has one processor and 15 hard disks. That rack has like 50 processors, but it's never the processor itself. It's like processor, motherboard, socket, all that jazz. Somebody came up with the idea, what if we make the processor ourselves and socket it in such a way that you can have the whole wafer for ourselves. It's like, don't even think about anything else. It's just like units, each unit connecting to each other without needing ludicrously complex things, without needing motherboard essentially. So they came up with this tile. Now the tile unit is that one big computation unit, and it has everything it needs. It's like it does not need to go fetch data from other cores, and the interconnects that they built is specifically built so it has ludicrously high throughput. So this is the highest performance one. Like, being very mindful, Cerebras is far more powerful than this puppy. However, this is designed a bit more of a what Tesla needs. It's a very in-house system, meaning what Tesla needs, how they can build it, how they can optimize it, everything is focused on Tesla. This on the other hand, Cerebras is a much higher grade equipment. This is more focused on, we're gonna sell this equipment to you. So be mindful. These two are the very big approach that people are taking, and you can even notice that in ARM architectures that are used for servers, the die size started with this. Now it's huge. So people are going to this bigger architecture. So like what Cerebras is trying to do is like ludicrously high. Like having this million cores is like, even graphics card don't have that many cores. So what we can expect in the future? Well, all this hassle we are doing through is basically we are fighting off Moore's law. Now, if you are not familiar with what is this is what we call magnetic core memory, meaning each of these beats, yes, they are big enough where you can see it with human eye, and these beats are bits. Basically, they can be on or off, magnetized or demagnetized. And yes, this is how we send people to the moon. Now, this is a 60-70-year-old technology, and we have progressed drastically. I don't even have to show you this hard drive where it's like, wait a minute, is that a water pump? Yes, that's how big of equipment it needs. Like, it needs this big motor just to spin the platters. So reality is we are fighting Moore's law, and we are doing it successfully. And at this point in time, the only time where we are truly limiting ourselves is the AI training backbone. Everything else, we got this. Weather prediction nowadays is good. As in India, if I get the newspaper that says there will be rain on 13th, there is rain on 13th. Like, that's how good we are at this point in time. But the AI is a new challenge, and this sort of technology, basically large scale CPUs, they can handle that quite effectively. So at this point in time, we do not have to worry about Moore's law anytime soon. And this is one of those technologies that will always work in the background. Do not expect to see this in your next system or even enterprise. This will be something very well suited for one kind of niche equipment. I can see that. I can see where people are using it for real-time physics simulation, because that's amazing. And I do expect to in future, like if we go to, let's say, 3 nanometers, even like 2 million core processor unit that is like crunching real time with that. Like data from hundreds of satellites goes into the system. It's like, yeah, the hurricane will move 3 inch from left, and then 1 second later, yeah, hurricane move 3 inch left. That's how accurate it can be. So there are some uses other than AI, but AI would be the most lucrative, so to say, part of it. But at this point in time, software has to catch up to it. Reality is, because it's very easy thing to say, oh, we have to redo the kernel, we have to redo this. It's a completely unknown territory for us. And this is time we are building something for something else. We are not building computer for ourselves, we are building computer for AI. So it's a different kind of mindset you have to think about it. You don't have to think about it like how a person is going to use it at the other end. You have to think about how a neural network is going to use it, how the heck it's going to facilitate machine learning. So this does require us to think a bit differently. And there is more than enough potential that people who like, quantum computer is going to replace silicon anytime soon. Yeah, it could replace it, but not happening anytime soon. So at this point in time, our future is kind of secure. Even with basically normal silicon, we have more than enough 20, 30, 50 years left, easy. Don't have to worry about anything else. So this was my presentation on big ass CPU. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.